Warren said, would you like to introduce Alexis? So we are here for Alexis's public defense. In our department, we have committee meetings, we have research defense, which is with the committee, it's been curated, approved by the committee, and now therefore this is a public defense for everyone, including faculty, fellow students, family, and friends. So with that, I introduce Alexis, and she'll do the presentation.
All right, thank you. Let's get started. Okay, and hello everybody at home. My family is at home watching Relax through YouTube right now, so I'm very excited that everybody could be here virtually as well as those of you who are here in person. Welcome and bienvenue to the best day of my life. But it's also, like he said, my public research defense, and I have to initiate my career. All right. So a couple of defense guidelines to do sometimes to things at the beginning. I'll give them to you now, and there's some people here who are maybe new, never been through defense before. So for today, defense attendance guidelines. First, make sure your sound is off. Make sure your phone is off. If anybody ruins my fantasy for the next 60 minutes, I might put you down for money. And but it's okay to have your phone out. It's okay to have your phone off. It's okay to get up. Just make sure your ringer is off. And if you really enjoyed something during today's presentation, I love snaps, and I think that that's like a good for the audio level. And so anything that excites you, please go ahead and feel free to snap. And then the third and final guideline is actually more of a dare. And since there's kind of a smaller group here, I think we can achieve this. I dare everybody to think of one question to ask me at the end. There will be a question section, and this is my defense. I am looking for a fight. So please ask me questions, and if I see you with your phone out, I'll assume you're writing down a question or taking notes. So without further ado, yes.
Questions in the middle or just
Oh, you can do them in the middle. Might throw off my flow. So know that like we'll have a discussion at the end. But if for some reason something is important to the understanding, yeah, definitely interrupt me. Committee is allowed to interrupt me at any time, obviously. And before I say another word about my research, I want to dedicate today's presentation to my mother, Amy Lowe Smith, who is watching this in her classroom right now. Hi, Mom. And to my grandparents, Tony and Janet Lowe. I have had no greater supporters than these three. So everything here today is to entertain and educate them because I love them so much. And to show, why all their hard work allowed this 11-year-old girl to grow up to play around in a lab all day. You've seen this in my promotional material. This is a picture of me at 11 next to my library assistant robot, Lars. Because I believed that in the future that libraries would have too many books for one person to navigate, so you would need an assistant robot to fly around and get the books for you. And this, I like this because it harkens to my first initiation with engineering, robotics, learning about it here in Northfleet Elementary School. And also around this time, really great movie came out called I, Robot. And if you haven't seen it, Will Smith plays a cool detective who rides a motorcycle and has a robotic arm. Very cool. I watched this movie hundreds of times on sick days as a kid. And things like this got me really, really interested in making science fiction a reality, thinking about how can robotics and humans interact, how can they interface, how can they, be used to help people be lazier in libraries. So this is my public defense. The title of it is Regenerative Bionics, Incorporating Reinnervated Muscle into Bionic Systems for Prosthesis Control. I think that's a good one-sentence summary of what's going to happen. The presentation today is we're joined by my thesis committee. I have 4 members of my thesis committee, including my longtime advisor, Nitish Thakur. And I also have Professor Warren Grayson, Sammy Safaha, and Gene Friedman joining on the committee as well. You guys have dedicated a lot of your time to listening to me talk about my research, so thank you guys so much. Outline. Today's presentation is broken down into 3 parts. Part 1 is cut wires. I'm going to talk about what muscle reinnervation is and how it relates to bionics. Part 2 is going to focus a little bit more on the muscle health, revascularization of it, and how bionic interferes potentially with healing. And then part 3 is just conclusions, final thoughts, a lot of acknowledgements, and we'll wrap it up. These sections correspond to chapters of my dissertation, which has been written and signed off on and will be submitted later this week. So if you really want tons of detail, that will be available to you for you to read at some point. This dissertation, though, is not just like some big original piece of work. It's actually a patchwork that threads together many pieces of writing that I've worked on and published during my time here. Some papers, so one review paper, one research article, and now a second research article that's kind of under construction. It's looking really good, got favorable reviews from its first round. And I also got to participate in helping edit a book chapter from Natika's Handbook of Neuroengineering and get experience filing a patent. And some pieces of all of these will be incorporated, as well as things from poster presentations I've given at conferences and proposals that I've written. So let's jump right in. Part 1, cut wires, investigating muscle reinnervation for bionics. So what happens if you lose an arm? It's not good, that's for certain. But could we actually give you a robotic arm today? And the engineer's dream would be to take the robotic arm tech and just plug it into an amputee's stump. It's plug in and you can totally replace your original arm. You're sensing what the arm is doing and you can move it very naturally. That is our dream, but that is not the reality. The current reality for amputees who do choose to use prosthetics to like grasp and move objects tend to use body-powered prostheses for many reasons. And so, but these have less joint mobility, but they're somewhat easier to control and you don't have to calibrate your non-electronic arm. And then there's an even bigger fraction of amputees who, for any number of reasons, don't have a prosthesis at all. So that was a super simple overview of the prosthesis side of things. What about biology? I've got a penchant for biology. What happens when you get an amputation? Lots of stuff is damaged. It is skin, muscle, bone, and nerves. Nerves being extremely important in this case because nerves are like wires to and from the brain. They're sending information back and forth, and they're going to be impacted by damage. Here's what's really cool about nerves and makes them different from the brain and other parts of the central nervous system is that nerves grow. And that is so cool. And there's a lot of people studying different aspects of this. And this is great because you can imagine, for example, if you break your arm and really damage the nerve and you lose some function, as long as you still have your targets, we know that the individual neurons wrapped inside of a nerve will start to sprout and try to make connections again with their original target. And that's great. Like I said, if you injure your nerve, you can rest assured that it has the potential to grow back and you might regain function. But if you've been amputated and you know that that target is gone and it's not going to be reconnected ever, actually nerve growth now poses a problem for you. It's the neurons are trying to find where to go and they're getting caught up in scar tissue. This forms neuromas, which can be extremely painful and make residual limb hypersensitive. So neuromas have to be dealt with. This nerve growth issue has to be dealt with for the well-being of the subject. And the reason that they're feeling pain, why they're sensing pain, despite the nerve being damaged, is because the nerve is still totally functioning in terms of sending electrical signals kind of back and forth to the ends, just like how a cut wire could still be live at the end. This is some benefits. In biomedical engineering, we make use of this to interface with nerves electrically because they both communicate electrically. We can use electronic interfaces to inject current into the nerve to elicit a sensory percept like a phantom sensation. And also you can record the motor signals that are coming down from the brain trying to move the phantom limb, and you could interpret those to potentially control a prosthesis. So these nerve cuffs, though, I'm showing you, this is an illustration, and I will say nerve cuffs are rare, but they are not science fiction. There are human amputees who have been implanted with nerve cuffs like this. So I have one example here. This is from a 2020 article in the New England Journal of Medicine, written by the folks at the Center for Bionics and Pain Research in Sweden. Big fan of their work. It will come up again. But this is one example of, they work with amputees who have osteointegrated rods. So we have these transcutaneous metal implants to help support when they're wearing their prosthesis, but it gives us a chance to also put electrodes into the body that can reach the outside. And so here you see, and this is the actual x-ray of a real person who has these implants, and they were used in some studies to do sensory perception stuff with prostheses. So, not science fiction. So what does happen if you lose an arm? Well, your nerves will regrow, but painful neuromas can form. So that has to be dealt with. And there's very few advanced bionic nerve interfaces specifically for regenerating nerve. Like nerve cuffs are kind of designed for just any nerve. It could be a healthy nerve, it could be a damaged nerve, but regenerating nerves have specific needs, and maybe we could take advantage of their specialness. And that's what some very smart surgeons, engineers, and scientists started saying basically around the time that iRobot came out. What if we use denervated muscle tissue, or DMT? That is an abbreviation that I will use a lot today. DMT, denervated muscle target. Can these DMTs be used as adapters to protect the nerve and to amplify its signal? The answer is yes. And here's how that works. It works through reconstructive surgery. So here's an example of a torso and like a residual limb that has cut nerves that used to have targets and now they don't. And then you also have normal muscles nearby that maybe used to be involved in motion that isn't necessary anymore. So you can do what's called a nerve transfer and take one of these nerves and move it over to this muscle after it's denervated. So this would be like an example of chest muscle, pectoral muscle, other types of muscles are used for this, but you just transfer it. And then the concept is that this nerve will now reinnervate this muscle. You can do this just by suturing it straight to the distal nerve stump. And they call this targeted muscle reinnervation. That makes sense, that's self-explanatory. And this was great because again, the whole concept is that the muscle is going to amplify the nerve signal to electromyography signals that we could detect. They're much bigger. So much bigger that maybe we could detect them from the level of the skin. That's actually kind of what the hypothesis was behind the surgery. If we use the regenerated muscle targets to amplify the signal, we could detect it from the level of the skin. So here's an example of I have a microphone on. Here's an example of a high density EMG electrode that you could put over the surface of somebody's skin and record EMG from many different contexts. And in this paper from 2014, they did just that. They looked at upper limb amputees who had targeted muscle reinnervation and recorded EMG signals from the surface of their skin. And they found that from reinnervated muscles, they were able to not only detect signal, but they could identify unique motor units, which if you're controlling a prosthesis, that just gives you a lot more to work with. So this is good and really promising. And what's more, the signals coming from these reinnervated muscles are correlated to how the individual wants to, like, say, move their arm. So here's an example of this. It's really nice because with the high density patches, you can see where the signal is the largest on the patch. So in this individual I'm about to show you, they've had their radial nerve transferred to some back muscles. So that's a nerve that would help you flip your palm up. And then here's another example. The ulnar nerve is more on their stump, and the ulnar nerve would close your hand, turn your hand down. And if we look at this individual who has these electrodes on, and then they're asked to lift your wrist down, and you can see that where the radial nerve has been implanted, that's where the activity is the highest. It's the same thing when you flip your wrist up or the other way. Which one's supination? Pronation, supination. And so you get the ulnar nerve activated. Great. So denervated muscle targets work. They've been proven to work. They've been proven to amplify the signals of the nerve. That's fantastic. There is one problem though. It doesn't always prevent neuromas, and this has come up a lot from surgeons I've talked to. So you can kind of see these nerves are the same size. So you can imagine that as the nerves are growing, they might start kind of missing their target, and that's how you could get an additional neuroma. And to deal with this, a second procedure was developed by some smart surgeons and scientists at University of Michigan, where they started using directly neurotized DMTs. So the concept is you can take a small piece of denervated muscle and just wrap it directly around that cut nerve ending. So there's not going to be any axonal escape because you're just directly making contact. You're not like making use of pre-existing neural, nerve structures. And additionally, lots of other researchers in this space have played around with this. And there's examples where you could also just have like a vascular leash. If you keep it vascularized, the small muscle graft doesn't have to be devascularized for this to work. But small devascularized muscle targets are really popular, and for good reason. But I will say small devascularized DMTs are also referred to as regenerative peripheral nerve interfaces in the literature, or RPNIs. So if you hear me say RPNI, think small devascularized muscle graft. So regenerative peripheral nerve interfaces came along, and they've been used in a very similar way. So here's an example of two individuals who have had RPNIs in the after a wrist disarticulation amputation, and they have multiple RPNIs. This person has 3, the person below has 4, and they've been reinnervated by muscles that used to operate the hand. Up here on the top, This is an individual who's being imaged via ultrasound, and they're being asked to like think about moving your index finger or think about moving your thumb. And the RBNIs that have been reinnervated by those corresponding nerves are activating, and that's really cool. We can see them twitching, and that's kind of like an extra verification on top of EMG signals. And this is just another video from that paper. This individual is controlling the hand and doing dexterous tasks using a combination of EMG signals from the reinnervated muscle and from some normal muscle. So, no two human DMTs are the same. There's multiple ways to do it. And so in the future, I think a lot of amputees are going to have multiple types of reinnervated muscle within their residual limb. So it's not like there's one way that's better. All of these methods in humans have been demonstrated to reduce neuronal pain. So there's benefit to doing all of these, and not just necessarily honing in on one that's best. Okay, so everything I gave you was an update kind of on muscle reinnervation, say in 2021. Now you're all caught up and it's 2020. And I joined the lab of Nitish Thapar. I'm here at Hopkins, and I come to Hopkins and say, I love implants. It's what I came here to do. It's what I'm really big into. I love materials and material biointerfaces, so that's what I want to do. And Nitish said, well, I know somebody. I know a surgeon named Connor, and he just came to me recently and said he wants to build interfaces. So I think the two should connect. So I met Connor and talked to him, and he was pretty adamant that we should develop specifically a interface for the small directly neurotized grafts. He was keeping them vascularized, but it's the focus on these small grafts that we should be making electrodes for. I didn't know how to make an interface, and neither did he, but that certainly didn't stop us. And it didn't even stop us that we were having this conversation in January 2020. Most projects I started around that time didn't make it. And this one, we really gave it a strong effort to design an interface. That was our original idea. And so here I'm showing some of my original sketches for the concept for a stretchable muscle interface that would be potentially adhesive, allow for regeneration. These are just concept drawings, but through these and other concept drawings and discussions with JHTV, we were able to file a patent. And Connor is successfully commercializing, this technology and licensing his patent, not in the same way as I'm presenting it, but still, something really valuable came out of this. And the concept was that, yeah, these interfaces would be used to control a prosthetic arm. But I don't know how to make an interface, and it's 2020, so, people are leery to start new spaces or start new collaborations. We decided to walk before we can run. We're both biologists. We're trained as biologists and not electrical engineers. So let's focus on what we have access to, and that's amazing surgeons, as well as access to fantastic surgeons who are training us, like Sammy Tafaha. So we're brainstorming. And I had this amazing undergrad student at the time, Maria, and she comes to me and she says, hey, do you remember this paper that you had me read? When I started the lab, and I said, oh, of course, yeah, I remember this paper. In the paper, they made RPNIs of different sizes. And then after 3 months of reinnervation, they measured the functional outcome. This is in a rat Heinlein model. And so they have differently sized little muscle grafts, and they would measure the functional activity. So when you do that in a rat model, you can't just like put a patch on a rat and ask them to flex. They have to be anesthetized, and it's kind of a surgical procedure where you go in and you find the reinnervated muscle and you apply your recording electrodes and you stimulate the nerve upstream, which forces the muscle to contract. And because it contracts all at once, we call that a compound motor action potential, or a CMAP. That is probably like the third abbreviation I'm going to use a lot. So CMAP, know that that's like a measure of function. Higher CMAP is good, higher force production is good. And what did these folks find? Well, they found that in their 4 differently sized RPNI groups, that as the RPNI mass went up, function went down, CMAP amplitude went down, force production went down. And the reason was because these devascularized grafts at some point get too big. Now it's too big, and now you have a core of tissue in the center that is not vascularized and is not being vascularized fast enough. So it dies, and you lose some functional tissue because of it. Well, Maria, being the smart person that she is, she said, well, I found a tetanic force sensor specifically for rats, and we can recreate this experiment using vascularized degenerated muscle targets, just basically making sure that the target is vascularized. And I predict that in VDMTs, as muscle mass increases, CMAP amplitude and force production will also increase. And because it is vascularized, it's not going to die when it gets too big. I was like, I love it, love this idea, great experiment. Also super impressed because at the time Maria was in Puerto Rico and she was finding me equipment to use here at Hopkins. So fantastic. She's at Michigan now. I did have a question though. I said, how are we going to measure the mass if we can't take it out of the body? It has to be attached to the circulatory system. So, well, we'll figure that out. And we're going to start by looking at our model. This is the first model of rat muscle reinnervation that I learned from, the Tapaha lab, and this was what they were using. It starts with the gastrocnemius muscle. This is a big muscle in your lower hind limb. It's your calf muscle. It's normally innervated by the tibial nerve, which is tucked back there. You can't really see it. What you can see on top is the peroneal nerve, which crosses over the calf muscle here in this case and goes to the shin. The peroneal nerve is the one that flexes your foot. So here's an illustration, so it looks a little less messy. Got all our components. Okay, so we want to see VDMT size and the influence that it will have on function. Let's go. Let's start by making a DMT. The way that we do that is you denervate the gastrocnemius. Boom, you did it. You've created a denervated muscle target. If we stop there, that becomes our negative group. So this is, if we denervate the gastrocnemius, wait 7 days, do our functional recordings, we expect 0 function. That's what we expect. Shouldn't be functional. So this is our negative group. Okay, well, we need experimental groups too. So put the negative group aside. After you denervate the gastrocnemius, you need to reinnervate it. So you cut the peroneal nerve and just suture it directly to the gastrocnemius. So it's directly neurotized. The muscle is still vascularized. Bada bing. And this is how we get our big VDMT group. And we wait 100 days of reinnervation because that's longer. We fully expect reinnervation to take place at this point. We want to look at size versus function. So I've got my big VDMT, and now if we want to make our small VDMT group, we're going to remove some mass. So because I can't measure the mass of the muscle itself, I can only measure how much I take out. So for every animal, we take out the exact same mass and do the same thing, then suture the peroneal nerve to the VDMT, and now we have our small VDMT. We've got our 3 groups for our first real experiment. We have our negative, our reinnervation negative, we have small VDMT, and we have big VDMT, and these are all being done in the left leg of the rat. So there are rats assigned to each group, and each rat has surgery in its left leg, and it has a totally normal, naive right leg. This is going to become our positive control for all the experiments, because this is what a normal gastrocnemius should be functioning like. So we've got negative, positive, small, big. Every animal had their left leg measured and then their right leg. So we would measure the function, take it out, weigh it, one on the next leg, measure it, take it out, weigh it, and then sacrifice meat. Okay, so now I'm going to get into results. Woo, we're getting into results. So there were 6 animals per group. I had 3 groups, remember? 6 animals per group. And the reinnervated muscle, their data will be represented with a triangle. In this case, the naive muscle will be represented with a square. And each group, I post the average, group average with a bar. Let's start with the first metric, which I think is important, which is muscle size. That's our independent variable that we want to test, so we need to measure it. So after reinnervation is done, we weigh all the muscles, and what do we find? Well, we found that statistically in the negative group, well, I'll say all the VDMTs are smaller than the corresponding naive muscle in terms of mass. And in the negative group, we did not see statistical differences, but that's okay. That's not a ton of time for the muscle to atrophy. Maybe that's to be expected. What wasn't expected, and what I even found to be like concerning or frustrating or many things, is that you'll notice the small VDMTs and the big VDMTs are the same size after 100 days of reinnervation. That was not what we expected. That was not what we were shooting for. I mean, we would have expected that the small ones were smaller, especially considering you can see their mass of a normal gastroc is around 1,500 mgs, and I removed like a third. So, but this was my first experiment. So we're going to keep going. We were methodical and we measured stuff. We measured the CMAP amplitude of these guys. We used a similar setup, put our recording electrodes in the muscle, stimulated the nerve upstream, and recorded the pulse. The maximum amplitude of those pulses is here. And you will see something that looks similar. Again, the negative VDMTs actually do have a little bit of a signal, 8 millivolt signal, which we'll say that's our background noise. That could be influenced by nearby muscle twitching or signaling. So that's like our background level of noise is at 8. And the VDMTs are producing CMAPs, so that's great. It's the same in VDMT groups and slightly less than the naive gastrocnemius muscles. Finally, after doing CMAP, we measured the force. So this is an illustration of like one of those Technic force sensors that Maria got us access to and we got to use. And these are the force results. In this case, the most striking win for the negative group is that it wasn't producing any force. So it was at least validated our negative group in this case. But the force production that we measured for small and big BDMTs was the same as the naive gastrocnemius muscles, which if you account for the fact that the DMTs, the reinnervated muscle, are smaller than the naive muscles, they're technically producing more force per milligram, but that's a conversation to dig into later. So this is what I found. I wasn't crazy about these results, right? I was like, this didn't really go how I planned. Let's try one more thing. Every left leg has a right leg. Every rat has two legs and they're paired and they should be similar because rat, it's from the same rat. So this is another way of demonstrating the data that will come up again, is that we do a measurement of the DMT divided by the measurement of the gastrocnemius. So I call that a ratio, or refer to that as ratio. It's always reinnervated muscle over the naive muscle. And because if the value is 1, they're the same, that the reinnervated muscle is behaving the same as the naive, and if it's greater than 1, you get it. And nothing exciting came from that either. The muscle mass ratios looked expected, CMAP amplitude, the ratios looked expected. The force ratio looked a little different, not super statistically different though. And yeah, these are the results of my first experiment. It's not everything. There's a little histology I cut out as well for time, but I will say I felt like, ooh, does this look like I don't know what I'm doing? If what I wanted to do isn't what happened. Well, what did I expect to happen? What did I really want in the beginning? No, we didn't get a small and a big group, but the whole point was that I wanted to see if in a vascularized DMT, do we see what we see in the devascularized DMTs and the RPNIs? As they get bigger, their function gets worse. So in a vascularized reinnervated muscle, we expect that as it gets bigger, its function should get bigger as well. And if you just plot all the data points, not based on group, they're color-coded based on group, but if you just plot them based on mass versus CMAP amplitude, you see the squares of the gastrocnemius are up here, and the DMTs are down here, so they're lower in mass and lower in function, and there's a good linear correlation between the two. It's not like super strong, it's not an R-squared of 1, but it is statistically significant according to a chi-squared association test. And if you do the same thing with mass and force, not as interesting, not as tight, which that's fine. Force could have some nonlinear equations to it. That seems totally normal. And girl, that's good enough to publish. So the idea that I was, we were able to see a positive trend opposed to a negative trend, touchdown. So we published our first paper. It ended up being in Frontiers, and Maria was my second author. And this was back in, we didn't get it published till 2024. The work started long before that. So what did I learn from our first experiment? Gastrocnemius muscle, not a good model for muscle reinnervation studies. The fact that I wasn't able to control the size very well, and I was a noob, I was a novice, obviously, but I wasn't able to control the size well enough that it was a good variable in this model. And the peroneal nerve also, which we were using, is not great for the model because peroneal nerve, when you cut it, the rat gets foot drop. The rat can't flex its foot anymore, and now they limp for, their future. And it seems that when muscle is vascularized, the size and the functional output are positively correlated. Seems like it. That's what the data seems to be showing. Maybe need some more experiments to fully conclude that. I need more time points too, though. Like if you think about it, I took one time point for the reinnervated muscles. It was 100 days. That's not the whole story. I mean, in rats, they might be finished reinnervating by 3 months. In humans, that's definitely not the case. And there's a process. It's a slow, long process of reinnervation that does take a long time. I also need a better surgical model for my rat studies. And I want to be able to measure the differences in vasculature in addition to other things. So, because again, vasculature size was my first independent variable, but now we're thinking vasculature may be important to keep as a variable because it influences how the reinnervated muscle will behave. And now we're going to part 2. Wow, I'm making good time. We're in part 2. What's blood got to do with it? Which is the effect of bionics on muscle graft revascularization. So we got to create a new model of muscle reinnervation. And I go, I'm talking to Connor and Dr. Nick Bongino, who was also in the lab at the time. And I was like, this is not working out. And they go, well, have you heard of the soleus muscle, which is another muscle in the lower hindline? And here you can see it. Here's the gastrocnemius. Here's a soleus. Soleus, much smaller, much more appropriately sized if you wanted to be like comparable to a human-sized reinnervated muscle. And it's got the nice things about this, especially compared to the gastroc, the nerve and the vessel are right there in the middle and super easy to find, even for a noob. And here in this surgical image, I've de-tendinized it. So I cut the tendons, and when you move the soleus muscle aside, oops, you can see the distal tibial nerve back here. So there's this big fat nerve right behind it. And if you cut that nerve, the rat does not get foot drop. So why don't we use this combination? This is what we're thinking, is use the soleus and innervate it with the tibial nerve. And in this case, they were like, well, we're doing vascularized DMT research, so we're keeping this vascular leash intact. And I thought, this is fantastic, and we should actually maybe try using the soleus distal tibial nerve for all the different types of reinnervated muscle. I could do a nerve coaptation of the soleus. I could do an RP&I with the soleus and do a VDMT. And in this way, I'm controlling for the muscle tissue type and source. And I have, and that way, my independent variable can be level of vasculature. So I have to test it, I have to make sure it works, right? So you have to actually see, does the soleus reinnervate in these different conditions? And I did some CMAP recording in our lab. And good news, it works. Shown here are average CMAPs. So this is average for, I think, 4 to 6 animals for the groups. And you see there's a positive signal. You can see it's smaller, maybe in the RP&I versus the nerve coapted group, but there is a signal nonetheless. So I say that works. That works. This model works, and we're using it. And Kiara, who's here today, I think so this was kind of my last EMG recording that you'll see in this presentation. Though Kiara's taken tons with this model and done a lot more than I was ever planning to do. So I thought, well, that's cool. You take that, you're good at that. I have a lead on some vascular imaging that I'm going to follow. I'm going to maybe get our methods up in that area. The method that I was really interested in is called micro-CT. So it's a little gruesome to get. You can only do it once. The way you do it is at the time of sacrifice for the animal, you stick a syringe in their heart and pump in a bunch of X-ray opaque polymer so that then I can take out the muscle, put it on a CT scanner, and get beautiful 3D images. And I was learning this from the Patak lab and the radiology department. So we had a really good workflow that we were borrowing from them, basically. And I want to measure, in addition to vasculature, this is past Lexi, I want to measure the EMG signals from different types of DMTs as they reinnervate over time. That makes sense. The signal will change over time. It needs to be minimally invasive, in my opinion, wireless, and longitudinal. We want to disturb the animal as little as possible so that we can collect data over this long course of healing. And we could combine vascular imaging data with electrophysiology data to build bioelectrical models. I'll talk a little bit more about that at the end, but this was kind of my motivation. So I need wireless implantable chronic EMG recording for my rat model. I said this years ago, and I worked really, really hard to try to achieve it. This was kind of what I imagined. This is from one of my many proposals, where the rat would be implanted with a wireless EMG transmitter, and as well as an electrode on their reinnervating muscle. And then the signal would be transmitted. We would record the signal. This while the rat was doing normal stuff, doing normal movement. We would record the signal and also record the movement, see how the rat was behaving, and track as potentially the EMG signal increase week to week. That was because that's what we expect, that it doesn't just go from 0 to having signal. There's an increase over time, and we're on a capture that. We got really, really close to achieving this, I want to say. Here I'm showing my motion capture setup that we did. I worked with many students who were really talented to build this stuff. So this is our motion capture rig. There's 2 synchronized cameras and a software that my master's student, Rob, wrote. Again, he's another one of my many remote students, and he built this totally remotely. I've really enjoyed working with some of my remote students. They're really impressive. And so I love this. This is our motion capture setup. It's modular, synchronized. And then we also have a motion capture model for actually tracking the joints, tracking the rat, where it is in space. And that was developed by another master's student who's working for me, Ashti. And so really, really grateful for the work they put in, because it is impressive. The last piece is the implant piece, and that's going to be my piece. So I did get some progress. I worked with a lot, I learned a lot about wireless implants. And I ended up buying some stellar commercial devices. So these are implantable wireless signal transmitters. You can buy them off of TSE. And I implanted a dummy device that had because you got to practice, right? Got to practice our surgeries. So I implanted a dummy device, and that is the rat you see here. He's been implanted with the batteryless device, but the leads still go down to the legs. And the concept was just to make sure I could do the surgery, the rat would survive. And this rat did survive and looked great for the rest of his life, basically. I was never able to replicate that success. It was not due to the technology. It was in part due to bad luck. It was also due to some failures of our surgical equipment, and it was extremely disappointing. Like, I'm not going to say this was probably the low point of disappointment for me in my thesis. I was feeling like I've been proposing this for years, and I feel like I had failed because I had two active devices, tried to implant them, never got it to work. So I will say it's not all sad. Luckily, I did get an injection of inspiration from the field. But before I talk about that, I have been talking for over 30 minutes, and I need a sip of tea, and you guys need a break from my voice. So I'm going to take a sip of tea and have a very special celebrity guest presenter take over for this next important part of the presentation.
Hello, my name is Nana Visitor, and I am so honored that Alexis Lowe chose me to read this list of mentors. You know, I just wrote a book recently about the women in Star Trek, and doing my research and the period of time that the shows were made in the 70s, 80s, 90s, and on, I really wanted to find out about mentorship, because my experience in the 90s in Hollywood was that there was one seat at the table, or that was the feeling, and you really didn't have a lot of mentorship from other women because there was a race for that one chair. And I found out in my interviews that it was pretty much the same in most systems. And the other thing I found out about my question about mentorship is the one that got it did so much better, had a smoother path forward, had a leg up, no doubt. And I also learned that the ones who didn't have any kind of mentorship or collaborative force around them as children, as young adults. They did something that breaks my heart and gives me joy. If no one around them supported their ideas for themselves, what they wanted to be and do in the world, they found virtual mentors on TV. They would choose a character from the show and learn ethics and see what worked and what didn't work, and think of that person and carry that person. I can't tell you how many people have said, what would Kira do? What would Dr. Crusher do? They keep that in their minds. Speak to the determination and imagination of the human spirit. Let me read this wonderfully long list of names. Reverend Penny Greer, Professor Barb Bell, Professor Deb Bauer, Professor Megan Nunez, Dr. Anya Yagilka, Professor Kristen Van Vliet, Dr. Leela Robluska, Professor Kathy Cullen, and Professor Nitish Thakur. I hope you all know each other and get along, because you are going to be surrounding this young woman virtually in everything she does moving forward. I really can't think of a more purposeful thing you could have done. Thank you from her and from me.
Can we give it a hand?
Yeah. So say we all. Okay. So you're feeling inspired and you're feeling really good right now, and you're ready to hear my voice again. So I said I was getting an injection of inspiration from the field that was going to pull me out of my slump where the wireless EMG wasn't working out. And that's from some human news with Reinnervated Muscle and Bionics. Here's another paper. So this was a more recent paper, a 2023 paper, again from the Center for Bionics and Pain Research in Sweden. We stand them. And this paper was led by Jan Spinden. And why I really like it was because it focused on one individual. This is one person who also had an osseointegrated implant. And what was fantastic about this surgery was that at the time of muscle reinnervation surgery, they also implanted recording electrodes. So they could record this individual's muscles going from totally reinnervated to totally reinnervated over the course of 2 years. The first year they did, every few weeks recordings, and then they did another follow-up at 2 years out. And so from that, they found they recorded from normal muscle, and the normal muscle had a signal. After surgery, though, you do get stronger, and the signal gets stronger. They did vascularized denervated muscle tissue in here, and it goes from 0 signal to big signal. And same with they did RPNIs, devascularized EMTs, and they go from 0 signal to big signal over time. I was so excited about this because I thought this is chronic monitoring of reinnervated muscles, signal changes over time. I have been proposing to do this in rats for quite a while at this point, so I was feeling a little validated. And there's something very interesting about this. So like I said, they implanted 12 electrodes. They have 12 EMG sources controlling that prosthetic limb. 5 of them are RPNIs, devascularized muscle grafts, small grafts, and you can see that they're different from the other muscles here. And what else is different about them is that there's some patch electrodes, epimysial electrodes for those of you who are familiar, and then intramuscular electrodes are actually being used in the RPNI. Rather than having a patch on top, it has an intramuscular electrode, which if you've read some of the research, people tend to like for chronic muscle recording patches because they don't damage the muscle tissue that's inside. So they kind of had to justify, well, why did we use different types of electrodes? And this is from their discussion section. The free muscle grafts are non-vascularized and are therefore dependent on blood diffusion from surrounding tissue for survival, although vessels within the innervating fascicle can also contribute. So that's talking about vessels inside of the nerve. The nerve has its own blood supply. Placing an epimysial electrode would compromise blood diffusion in a relatively large surface area, and therefore intramuscular electrodes are preferred for this muscle target. So those 2 sentences are straight out of the discussion, and they don't have citations, which I was like, that's a little disappointing because the citation would help me kind of like validate what they're saying. And however, this was co-written by some of the co-authors are surgeons. And as a surgeon, I think this is a totally reasonable thing to say. You're going to put a devascularized graft in somebody, you would never put a patch on top of that. That seems, not responsible. So this makes sense, but it wasn't being backed up by evidence. And I did a little hunting. I wanted to look through the literature and see what I could find. I found 2 examples of rat studies that did this, and made an RPNI and added a patch to see what would happen. So there's 2 examples. One is from a paper in 2014 written by the Michigan folks who do RPNIs all the time. Another paper is from 2019 when Shreya Srinivasan was at MIT. So same model, different person, different lab, different state. And they both used the EDL muscle and the peroneal nerve to make their RPNIs. And they had patches involved that were chronically implanted for at least 4 weeks. Stainless steel patch on this side and polyamide patch with gold contact on this one. The results. So they made RPNIs, they put on a patch, and what did they find? Well, they found that after several months, the muscle looked fine and actually healed. Both studies showed RPNI muscle survival, and they also said we can see vessels. When you take a cross section of a muscle, they can see capillaries. They have a clear, morphology. So they're saying this muscle is vascularized and it's functional. They also recorded the EMG signals in both studies and found that there was CMAP amplitudes that were detectable, very detectable. So that doesn't seem like patches block RPNI revascularization, but it's still a concept that we always talk about and you definitely hear a lot about when you're talking to surgeons. So knowing all this information and the inspiration I got, how should I direct our next investigation? Well, I've been wanting to do chronic monitoring. I really want repeat measures from the same sample over time because I want to track its progress. This is not like a one and done situation. It's a change over time that we want to measure. Vascular everything's looking pretty good. Those are like our CT scans. I was like, wow, that's amazing. Wireless EMG, not so much, not working out. So how do we direct ourselves from here? There are many unanswered questions about RPNI revascularization, and it's critical. Like there are humans who have these surgeries and are being implanted. It's a question that needs to be addressed on some level. Because in humans, RPNIs only get intramuscular electrodes, but in rats, patch electrodes, while rare, have been shown to show survival. And it's not to say that like patch is definitely a better type of electrode than intramuscular, but I think you want to have variety, you want to have options, and there's other reasons why you might want a surface electrode. So how can we study this to make more types of electrodes available to people working with reinnervated muscle? Anyway, speaking of vascular imaging, I was like, hey, I have a good idea. Hey, Max and Dennis, don't you guys have an ultrasound machine that can measure blood flow? Which they do. It was in our lab. I know it's a retired clinical machine that's owned by Professor Amir Manbachi, and they very graciously let me use it. So now I'm beefing up my vascular imaging material, my methods. So here, this is my surgical bay where I work. This is the Canon Apollo machine, and here's my little rat buddy, and he's got ultrasound gel on, and we can take images, live image monitor, we can take videos, and we can also do Doppler, so we can look at blood flow within the muscle. And this is fantastic because it's non-invasive, it doesn't hurt the animal, so it won't disturb the blood flow. This is great. We started collecting ultrasound data as soon as I figured out how to use the machine. And I have a fantastic, another graduate student of mine, Maria Isa, another remote student, she's in Switzerland right now. And so she's been helping me process all this data. Okay, so we've got our model, and we've got some vascular imaging methods. We've got the ability to make an RPNI out of the soleus and the tibial nerve. We've got cool ultrasound imaging. And in addition to the ultrasound imaging, we also have the micro CT. So not only did I have those raw scans now I also have a master's student, Deanna, who's fantastic and much more gifted at coding than me, who has helped me process those scans. So that now we have these really clean vascular trees that we can break down and analyze. I thought, who the heck is doing this? Nobody, just us? That's great. We can measure how RPNIs revascularize in 3D during the early days post-surgery, which I predict is from the outside in. I hadn't really mentioned that up to this point, but as far as we know, muscle revascularization, if a muscle is grafted, taken out, put back in the body, vessels will start to grow, and they will tend to be more concentrated around the surface. But nobody's been able to do 3D vascular imaging like this of muscles that have healed. So, but you're only seeing 2D cross sections, you're not getting the full picture. But now we can do it in 3D. So we did such an experiment. We measured rats who had soleus RPNIs in the left leg. We took them down early. So vascularization has to happen in 2 weeks. That's way faster than reinnervation, which takes like 3 months. And, the clock was also ticking on graduation. So this seems good. These are quick studies. 5 days post-surgery, perfuse the animal and look at how the muscle is healing. And same thing, 10 days post-surgery. We also did 15 days post-surgery. That's closer to the 2-week mark, but none of the data showed here because the micro CT didn't work out. I will say perfusion, very hard to do. But regardless, I do have data for these. So 5 days and 10 days post-surgery. We're gonna have some similar data breakdowns as before. So first, vascular volume. How much vasculature is there, period? Like if we just measure the volume in voxels, what is that? Well, I'm gonna walk through the graph. So again, squares are the naive, right, soleus. Circles are the left RPNI. They're divided by day post-surgery, so 5 days and 10 days. And as again, every rat has a left leg and has a right leg. And so we also do ratios where I divide the GMT value, the RPNI value, by the naive muscle value. So we get these ratios. So let's look at this first one I have, vascular volume. Okay, let's see, on average, from day 5 to day 10, the vascular volume goes up. That's not statistically significant though. So we can't say that that would hold. Like we might gather more samples and find that this pattern doesn't hold because we see so much variation here. It is though generally less volume than the naive muscles. Full volume of the tissue, so that's just measuring like how big is the tissue itself. We expect that RPNIs over time are going to shrink. You've heard of muscle atrophy. If a muscle is denervated, it starts to shrink. So we would expect that on day 10 post-surgery, the RPNIs would be smaller relative to naive soleus than at 5 days. So we do see that, and that is statistically significant that we can kind of observe atrophy through this. Nice little validation of the model. And because I have vascular volume, the full volume, now I'm going to measure what I call the vascular fraction, which is just for this study, the vascular volume divided by the full volume. And this is an underestimation, right? This is not the exact blood volume that the rat would have because it was perfused after death. It didn't have the same pressure. That's just a little note. Anyway, vascular fraction, we see the percent of the volume that is covered by vasculature in the RPNI groups does go up from day 5 to day 10. On average. So that's great. And not statistically significant again, but kind of preserved. So it's hinting in the right direction, but there's so much variability within the groups. Like you can see this spread of the one sample really high, one sample really low. It's that's what affects the statistics, and this is actually kind of normal with I'm finding out with animal work. Okay, so in addition to looking at like the whole tissue properties, I'm also able to segment. There's a software called Amira, and again, thanks to the Kasaka Lab and their resources that we get to borrow. I use this to divide the volume into individual segments. So it finds the branch points in all of these vessels and then divides them up into sections. And I can look at the statistics of those sections. So then I'll call them segments. The number of segments actually goes up quite a bit, not statistically significant though. So like, don't think that this trend is set in stone, but on average it goes up a little. The total number of segments ratio doesn't really change. I would have maybe expected the total number of segments to increase, and I think it did on average, but not a ton. The median segment length did not change very much between the RPNI day 5 and day 10, but also not very much between the naive muscle. So that's making me think that just the segment lengths themselves is not, I don't know how much it's telling us here. We need more information. So that's that for the segments. Okay, one last thing that I wanted to look at was because I had talked about my hypothesis was that vascularization is happening from the outside in. So at day 5, there should be more vasculature outside than at the core. And on day 10, there should be more vasculature in the core than there was on day 5. Let's see if that's what happened. Well, here is on this side, percent of vasculature in the core, and the percent of vasculature in the outer shell. Actually, in the core, did not change from day 5 to day 10. I was like quite shocked by how much of the vasculature was in the core for day 5 RPNIs at all, and percent of vasculature in the outer shell, slightly higher on average, nothing crazy. And so this was the outside in model. I did one other thing where I wanted to just have the muscle and chop it into sections and look at like top versus bottom, which I call distal versus proximal. So in the distal section, which would be the bottom, we don't see much change from day 5 to day 10 in the vasculature. In fact, on the ratios kind of trends downward a little, but we did see statistical significance in the proximal region. So that's the top of it. Significant, pretty, like none of the patterns have been quite so strong and striking as this one, where we're going up. The percent of vasculature contained in the proximal section is increasing from day 5 to day 10. Do I know why that is? I don't know for certain, but I have a theory. And my theory is what was mentioned in the discussion paper of that, or the discussion section of that previous paper, is that the nerve might be contributing. In this model, the distal section of, or sorry, the proximal section of the soleus has fascia that's nice to anchor to. So I tend to suture the nerve closer to the top. And that's where we're seeing an increase. So, one of the few statistically significant increases from day 5 to day 10. And that's very striking. That makes me think that perhaps the nerve really is contributing something, or the act of suturing it there's maybe some pro-angiogenic stuff happening, and we should investigate further. Last thing from this phase is that we wanted to look at the micro-CT and the ultrasound. Do they relate? Could they be related to each other? Because the micro-CT is very clean and crisp and clear, and the ultrasound is a little lower resolution, can't see quite as much, but we wanted to, can we find commonalities between the two methods? I will say it is nice. You can see main vessels in normal muscle. This is a normal soleus, and you can pretty much see where the main vessel is, both in vivo and ex vivo. This is an RPNI from the same animal. A little harder to tell with RPNIs, but pretty clear to see the attachment site. I know that's the medial side of the muscle, which is where I always do the attachment. So we see a lot of blue, high blood flow at the attachment site. And we see that again, this is a different rat, same study, and you see the same pattern. We're able to find the main soleus vessel in the ultrasound that is reasonably identifiable in micro-CT. And then the RPNIs also have a really active attachment site on that medial side. Okay, so how do RPNIs revascularize immediately after surgery? I'm trying to answer that question for us in the field. And I'll say quickly, patterns set by day 5 post-surgery. That was shocking. The amount of vasculature that I saw in RPNIs at day 5 post-surgery kind of surprised me. And definitely the amount of the vasculature that was in the core surprised me. Because we've been told like it takes 2 weeks. So I was thinking it was just going to encroach slowly for 2 weeks and then be done. That's not what I saw at all. And based off that fact, that there is vasculature in the core of the RPNI by day 5, and that percentage doesn't change from day 5 to day 10, that makes me think that it's because the volume of vessels is increasing from day 5 to day 10, but the fraction in the core is not. So to me, I visualize that as vessels reach the core as quickly as possible first, and then add on volume, add on more segments. So they go for distribution before focusing on volume. Try to cover as much of the tissue as possible, then add on more segments. That's my working hypothesis right now. And also, I think the nerve attachment site might be creating some kind of pro-angiogenic hotspot that needs to be further investigated. So this is my last experiment. I thought maybe I can manipulate the RPNI revascularization pattern in more than one way. So this was what, for our previous data, we had a unilateral RPNI surgery, meaning they just had surgery in the left leg, and there's no like implant or anything. This is what we were just talking about, 5 days post-surgery. I'm going to stick to 5 days post-surgery because that's short and it makes my work faster. So we're going to stick to the 5-day time point. And we're also going to do now with a new cohort of animals, all those animals are going to get bilateral surgery with implants. We're going to use patches, and we're going to use materials that would be normally used by other people in the field who want to make a muscle electrode. So I've got polyamide with gold. I have these lying around the lab. I have silicone from a microprobes electrode. These were things from my early days where I was really ambitious and thought I was going to make an implantable wireless interface. Well, make some use out of them. I turned them up and implanted them. And I wanted to make use. I wanted to have a lot of samples with implants. So that's why every rat is bilaterally implanted, because you get 2 legs, you get twice the data. But I wanted to do something a little interesting and see what would happen, because we think the nerve is maybe providing blood flow, and we think that the patch is blocking it. So in this case, for the rats, on the left leg, I'll place the patch and I'll put the nerve under the patch. So, right, this is like trying to cancel out. You've got the thing that's blocking it, but you put something that's contributing positively underneath it. Maybe you'll cancel out the negative effect. That was my thought process anyway. And then on the opposite side, we'll have the nerve on the opposite side. See what happens. This is what it looks like on micro CT. So I think I have 5 animals in this group. The gold shows up kind of nicely on CT, which is cool. The polyamide does not. Silicone shows up kind of nicely too, but they're thicker in this study. I got some results. So vascular volume over total tissue volume. So that's that fraction I mentioned in the beginning, what percent of the full volume is vasculature. And the implant RPNIs have significantly smaller fractions than the naive soleus, but they are not statistically smaller than the RPNI without implants. So statistically, you could say that the implant didn't block the vascularization at all. I wouldn't say that, though. I wouldn't say that. Because of this. So I was talking about segments, right? I had a hypothesis that the goal of revascularization is to send vessels as quickly to as many places as possible and then build on that. And this data is, actually this one is statistically significant. The median segment length was longer in the implanted animals, and the total number of segments was smaller. So you can imagine if you like laid down a highway and that's one long segment. But then if you start adding branches to it, now these become individual segments, and now you have more segments and they're smaller. And here we have fewer segments and they're longer. So this is like a pattern that is somewhat supporting my hypothesis. Again, because of all the high variability in this data and micro CT being only one way of measuring this, I'm not 100% confident in that, and I think we need to study it more. I went ahead and did that core versus outer shell thing for the implanted animals just to check. And their percent of vasculature fraction in the core at day 5 post-surgery is less than the other groups. Slightly, not statistically. Again, it's on average, it's not statistically significant, but you see a trend, and you see that the vascular fraction in the outer shell percent is slightly higher as well. Well, we're getting a really clear picture here. Last thing, the 2D ultrasound images that I showed you in the first phase, I wasn't super satisfied with those because it wasn't giving me quite enough information. So I worked out a method to do 3D ultrasound, which was very easy. I took a picture and then slid the probe to the picture, slid the probe to the picture, did that, and created a 3D ultrasound volume, which is great. So this is an example of like the full volume. It's got thicker slices because me sliding down the slide has lower resolution, but I was able to do it for both V mode and Doppler. So I can get a 3D volume in the ultrasound, and I can also get kind of a flow map, a 3D flow map, which I wasn't able to have before. Now this is flow velocity, because Doppler is telling you about like the speed of something moving, and it's really only telling you about the speed of things moving toward and away from the sensor. But it's still information, right? If there's no blood flowing there, you wouldn't have any Doppler signal, and a lot of Doppler signal means more blood flow usually. So let's try to use that. This is measured from ultrasound, not from micro CT, from ultrasound, the total tissue volume. So in this case, I did it longitudinally. I took measurements on day 3 and day 5. So we have the measurement at the end, but we also have a pre-measurement. So here, this is yellow is that RPNI with the nerve under the patch. Purple is opposite side of the patch. And then diamonds are day 3, circles are day 5. Total tissue volume, nothing really crazy or interesting there. By day 5 post-surgery, you actually wouldn't expect much change in volume, so that's fine. Again, atrophy takes a little bit of time, so not seeing big changes there, no big deal. But what I was really impressed by was this. So I took everything here that's positive, I call that Doppler positive. If you set off the Doppler, radar, you're Doppler positive. What if I take all of the voxels that are positive and divide that by the total number of voxels in the volume? So I'm creating a kind of fraction. It's different, the thing I'm measuring is slightly different, but the concept is the same. I want to see how much of the volume has been kind of infiltrated by areas of high flow while the muscle is healing. And here was like some statistically significant results. From day 3 to day 5, in both groups, the Doppler positive volume, or the Doppler positive fraction of the volume increased statistically significantly. Oh my gosh, I rarely get that. So I was so excited, and I think that this to me is something I would love to keep doing. Like if I had more time, to do more time points, do more measurements like this, because the ability to track the revascularization non-invasively in a rat, I mean, I'm very excited about that and think it could be built up and we could do so much more. But I do have to graduate. So do electrode substrate patches block RPNI revascularization? Well, not exactly how we thought. I mean, the way I would talk to some people about it, they were imagining that like it's just straight up blocking, nothing can get around or through having this patch there. But that's not really true. It seems like the revascularization is slightly attenuated, but it's not totally blocked per se. We would still need to do a little more investigation to declare that. And 3D ultrasound imaging is sensitive enough to non-invasively detect vascular changes over time. Ooh, that's exciting. We've reached part 3 now. Wrap it up. So now I'm just going to say the wrap it up section. So I have this kind of structure. So, I'm going to give my final thoughts. And I'm going to give a lot of acknowledgements because I did not do this work by myself, as I've been alluding to. And then we'll have Q&A. And that's where, if you ask a question, get a special treat. Then we'll have some committee deliberation. I'm going to talk to my committee. This is kind of normal to have a little break. And you guys can refill your drinks. And then we'll come back, have some concluding remarks from Professor Tuckworth. And then we'll wrap it up and we'll just have a big party. Okay. So next steps for this work I presented, if people in the lab wanted to keep doing it, what should they do? First thing I would say is hotspot analysis. This is something that I kind of had come up with Deanne and Martin, the 2 master students who are working with me, is this idea that you want to look like, what is the vascular density in this region versus this region? Is there a hotspot? Is there an area along the surface of the RPNI that's really getting all the vasculature and one side that's getting none? We need to do more kind of like volumetric 3D type analysis to confirm that. And this would be able to say more to us about what the patch is doing in 3D, because it's much more complicated than just blocking revascularization. I also think chronic EMG with longitudinal ultrasound imaging would be a great study. I still think it's worth it. I did do ultrasound on this guy, and you can see the implant and track the stability of the implant. Just because I failed, it doesn't mean it can't be done. Certainly doesn't mean that at all. So I think it's worthwhile because you could be replicating human studies in an animal model, and that has lots of benefits because animals we can get more advanced data from. And then my third and final thing, testing the effects of electrode design changes on revascularization. So I just used patches. Why does it have to be a patch? It doesn't have to be a patch. There's not contacts all over the surface of the patch. It could be porous. It could be a mesh. It could have all kinds of things. And so these are ideas They're not gonna be copied exactly or like taken exactly, but I will say Alessandro and Pierce are two PhD students in the lab who like continue this work and kind of do variations of this. So the work's not totally over. Story's not done. Big picture things. I just want to give some thoughts about kind of what I think about all this, having not knowing anything about muscle reinnervation, and now I'm defending my PhD talking about muscle reinnervation for bionics. I think that muscle reinnervation should continue to be studied in animal models. We should continue to be standardizing it. You know, like we've had a few different models of reinnervation in the literature, but some of them are similar and some of them are easy to replicate. We could really share those and get a lot better data and make better conclusions, make better data sets. You can do so much with rats. You can do it high throughput, kind of have more data. Second, I mentioned this before, bioelectric models can be built from this data. Like, why do I think you should collect data from rats? Because you can collect way more detailed data and standardized data from rats than you can from humans. You can do the same surgery the same way in rats, which you wouldn't maybe do in a human. And so you can collect data that will give you really clean data that will help you build a model. And I would call this like the Myo model. But the concept is that you would take physical, you could learn, so let's say if you have imaging data and you have electrophysiology data, you can understand how the structure of the muscle is leading to the function. And then if you have enough data that connects those two things, then you can start to predict based off how the muscle looks, how will it perform. That could be very important for a human amputee who's going to be going in for an RPNI surgery and they're fully anticipating that they want to interact or they want to have a prosthesis in the future. You know, maybe the surgeon wants to understand more about if I do this versus this, how would that affect the long-term function? Because in the operating room, I don't know, the muscle's devascular. Could we predict what it will be like after it's reinnervated, after it's reinnervated, how will it function? And finally, I've developed a love for non-invasive techniques because they give us better longitudinal data, I think, which should be shared. I have loved using ultrasound in my PhD. I've used it for a few things in addition to this work, but I think it's got a lot of promise, especially because of its non-invasiveness. I also think that the circuit CMG stuff I've talked about before, well, I mean, it hasn't really been tried too much for RPNIs in humans, not that I'm aware of. And I think, especially with these folks in Sweden, you know, who go to do the studies in Sweden who have osteointegrated rods and implants, I think that this is potentially a missed opportunity for ultrasound. For these folks, I haven't seen any ultrasound yet. And I also haven't seen any surface EMG from these folks, because I would love to, for example, if you have an implanted electrode recording from a reinnervated muscle, and then you could also maybe put a surface electrode and compare the two. And the whole point of that, like I told you when I came to Hopkins and I said, I love implants. And now I'm thinking maybe non-invasive is the way to go. Maybe achieving this future is actually not going to require implants at all. And we could focus on, you know, non-invasive things because there's more than one way to do it. So this is it. Okay, so I'm going to do acknowledgements first because I did not do this alone. I mentioned them at the beginning. I'm going to mention them again. My mom and my grandparents have supported me so much, and I just have to thank them again. I'm thanking you guys so much. I love you. And I'm just so proud of them too. Like my mom was the first woman in our family to get a 4-year college degree. And in 2019, she became the first woman in our family to have a master's degree, which kind of like, Mom, I was going to be the first, but I'm still super proud and happy. And this isn't the whole story. This isn't my whole family. I have other family members who also help me. And thank you guys so much. I know you're watching. I love you guys. I'll say my stepdad, Chris, for example, he's the one who taught me how to use power tools so that I could build Lars, the library robot. And also my dad, you're watching. Thank you for making me tough. I love you guys so much. Thank you, my lab mates, fashion professionals, and people who act. My family didn't do any work, but you guys did help me. Thank you, my lab mates. I've enjoyed being in the Popcore lab. It's a big lab, it's diverse, and I've learned a lot. I've enjoyed hanging out with you guys and growing as people. And I want to do an extra special thank you to Johnny, who's here. Johnny has been like my lab partner, my research partner. She's done so much, and I was so happy when she joined. And yeah, well, she's been a partner, been a co-author. So grateful. Thank you, John. Thank you to my collaborators. Yes, the Tafaha lab, of course. I never would have learned how to do rat surgery if not for the Tafaha lab. I'm grateful to have those skills. Who knows how they'll be applied in the future. And of course, Professor Patak's lab, who I mentioned, his students have been super gracious in teaching me how to do vascular imaging and vascular analysis, which was not something I necessarily came to Hopkins to do. But now hey, you never know what you're gonna learn. Also, Taewon Chun's lab at Bayview and Taylor Bopp, they helped us do those force experiments in the beginning when we were just kind of like babies. And of course, Professor Amir Manbachi, who graciously let me use his ultrasound machine for our studies. National Science Foundation, I received a graduate research fellowship from the NSF, and that funded my 3 years of my salary. So really, really appreciative of them, because a lot of this work is less well established. So it's very nice to be supported. Thank you to my students. These are the folks who I'm like amazed had worked for me, because they all on volunteer or on the promise of authorship. And they've been so fantastic, whether I fulfilled my promises or not. So graduate students, I want to say Jackie Chan, Rob McDonald, Maria Isa, Aki Jane, and Deanne Chen have all done fantastic things for me that, like, there's stuff up there that would not have been done without them, period. So I'm super grateful to my team and to my undergraduate students. Half of undergrads in front of me. And you guys are so fierce and competitive and want to be in the lab, which I love. So thank you so much to Anna, Maria, Claudia, even, and Avanish. I really appreciate you guys so much. You make it fun to work here. And thank you guys who are here. Some of you were already on the other slides, but thank you guys anyway for coming. Thank you guys at home for watching. And this concludes my research talk. Who's got a question?
You will orchestrate, or would you?
Okay, I mean, so go ahead, anybody got, and of course the committee has person. Yeah, Eric, please.
First of all, lovely presentation.
Thank you.
I didn't do.
Oh, thanks.
I was gonna ask, why did you not try the skin EMG transcutaneous?
Oh, on a rat?
Yeah.
Because I didn't really have that capability, but I would love to. It could be done. So let's say, like, if the rat is anesthetized, they're asleep. The question, by the way, was why didn't I try doing surface EMG on rats? It could be done. I didn't necessarily have the electrodes to do it, and the rat would have to be anesthetized. You have to go inside anyway to access the nerve to stimulate. So if you really wanted like a true EMG, surface EMG from a rat, you have to like make a little outfit for them with EMG electrodes in it and have them walk around. That's a great experiment, and somebody should do it. But yeah, hard with rats. I would have loved to have met more humans to interact with, because I think that's where that's going to really be done the most.
You measured force output in the beginning, then you kind of stopped measuring force output.
Mm-hmm. It was, so actually the only reason we did force output was because that paper Maria brought up, written by Hugh and his colleagues, I think it came out in 2021 or 2020. Anyway, they did force. They did CMAT, and they did force, and they did histology. And we said, well, we're trying to prove that if we make a few changes to the surgery, we'll see a totally opposite trend. You need to do the same metrics that they did. So that was kind of, and we felt that that would be supported, would help it be more publishable, because like we're trying to reproduce methods at the same time it shows something new. Thank you. Yeah, Jean.
So your vascularization question as to why it gets revascularized all over.
Mm-hmm.
You know, this highway hypothesis where it goes make big blood vessels coming out.
Mm-hmm.
Let me give you an alternative hypothesis and tell me why one is better than the other.
Okay.
And if it's not, then how would you go an experiment to differentiate between the two? So the alternative model could be that you have vasculature already existing inside of this piece of muscle.
Totally.
It could very well be that you are using the existing vasculature as is, right? You're not growing it new. So, so would you expect one hypothesis to be better than the other? Why? Then can you tell me an experiment that you would do to differentiate between?
Well, what you bring up is interesting. If anybody couldn't hear the question, it was kind of about my hypothesis of revascularization, which is, the muscle used to have vasculature inside of it. What if some of those structures are still preserved and being capitalized on by the revascularization process? Totally possible. I think that it had been proposed in some of the historic literature. I'm thinking specifically, there's this review paper from 1994 I was reading, and they were talking about all these historical studies of muscle regeneration. And there was just one sentence in that review that said, maybe there might be existing structures still present. It seems like when we look at cross sections of these muscles, that there is vasculature in the center on like, day 3 or day 5, we think that's leftover. We don't think that's new. We think that's left from for the previous existing structures. Maybe it hasn't been broken down yet or whatever. I think it could be done. I would want to do some kind of experiment that, let's see, how I would want the experiment to somehow tag all the vessels that the muscle has when it's a naive soleus, like somehow mark those naive vessels, and then do the surgery, do the RPNI, and then after some revascularization time, take it out and see if any of those markers are still there, if they've been digested out, and if the vessels we see in the center are new, or some other kind of variation of that.
How would you mark it?
It's funny, so I'm a neuroscientist. One of the things that comes to mind are types of markers you can incorporate based on the native behavior of the thing. Like I'm thinking BRDU, like that's something you can inject while they're alive and then later go and see like how things changed since you injected that, like how the neurons, usually in the brain in that case, changed. And with the techniques I have, I would maybe want to do some more 3D vascular imaging. Maybe if I could enhance my ability to perfuse the muscle, because my perfusions are okay, they're decent, but like if we could really get good perfusion on like day 0, day 1, because if there's structures on day 0, I mean, I guess I think we can assume that maybe those are still existing. So maybe I would have to do some more research, but that has totally been proposed, and I can totally see that being a possibility. Any other questions? Yes, Becca.
So you looked at a bunch of different imaging modalities throughout your PhD, which is your favorite? And is it ultrasound? Because you seem to like really highlighting it again.
I love ultrasound. And maybe I'm biased. When I did do my first rotation in Kathy Cullen's lab, she worked with monkeys, and so I did like 4 months of monkey work before I came to the software lab. And she wanted me to do ultrasound on her monkeys, and she wanted me to look at the muscle activity because they were doing some vestibular stuff. And that was so fun to like train for. And so as soon as I kind of saw ultrasound being used in our lab for other stuff and spinal cord folks, it's like, we should be using that because there's definitely translatability. Like you would never be able to do micro CT probably on a primate. I couldn't see how you would be able to do that. It would have to be very special. And it's a terminal thing. So ultrasound, it's in vivo, it's non-invasive, like it's not disturbing anything, and you're getting such a beautiful, clear picture in some cases. Downside though, the big downside, gel. No gel, no picture. And so those rats, when I take the pictures, I like slather them with a big dot of gel, like drop it on, and then I lower the probe into it. If you don't have good gel, you're not gonna have a good signal. So that makes it hard for like wearable stuff. Because I would love the idea of like, you've got a wearable ultrasound sensor that's telling you how your muscles are behaving, but that's not possible without some kind of gel-free scenario.
And then when you did your 3D slices, the ultrasound imaging, did you do any normalization or or how did you? Because I know you said you were moving profile.
Oh yeah. So for that, I just did. Well, it wasn't by hand. I have so it's a slide. It's on a probe holder, and it has a stereotactic frame, and I can turn the knob, and it has a ruler. So I was going every 0.5 millimeter, which was as good as I could do. Maybe could have done 1/4 millimeter, but would have been tricky. If you have an automated one, there's an electronic sliders you could get, and you get super good accuracy and resolution. Or you could buy a very expensive rat ultrasound machine that does the 3D ultrasound on rats that I demoed. It's more than $1, so we obviously don't have that. Yes, Sherry?
I guess you guys can kind of answer part of it, but I was kind of wondering how much does the inflammatory side of things right after surgery, like as far as the revascularization, post-surgical effect and thing, whatever the residue left, how much does that affect revascularization?
Can we repeat the first part?
So I guess based on when you first have the surgical intervention,
Yeah.
maybe some sort of inflammation, other stuff.
Yes.
In the region, how does that potentially vary between different rat models, affecting the revascularization?
Right. So the question is like, if I've mentioned how many different ways there are to make a DMT, would there be some scenarios where like the DMT could be affected by the surgery differently and that might influence revascularization? Maybe, but I'm thinking maybe not so much. I mean, in the case of, and I'm not actually a revascularization expert, there's people who like the angiogenesis and vessel growth, that's like their whole thing. And I have read a few papers where I know, for example, how revascularization happens. I've talked about how like when vessels are first revascularizing, they'll be really windy, and that actually makes it easier for new branches to come out. And then later, cells will come in and straighten out the vessel. The vessel will become straight. So like things are changing based on some kind of chemical signaling that we're not fully aware of. And there are a lot of pro-angiogenic markers. I would say maybe the wound bed. The wound bed is probably the biggest influence, not so much the muscle itself or what's going on, but like I've seen experiments where if you put the graft deep surrounded by muscle, like deep in there, it'll revascularize nicely. But then you do an RPNI close to the surface of the skin and it dies. I've seen some rat studies that had examples of that. So like you kind of want to be surrounded by the blood, like the blood that's sitting in the wound bed, because that's full of white blood cells that are going to come in and clear out tissue, as well as like full of pro-angiogenic markers that are going to cause vessels to grow.
I guess following up. So, if muscle mass is staying the same, would vascularization drop in the future? Maybe like post whatever.
That's a good question. I kind of have some, because I told you I did 15-day animals, but I only had 3 that kind of worked out, and the perfusion wasn't very good. But like they had lower vascular volume. I'm trying to remember. I had another thing too, where like and it was maybe one of these figures where like on day 10 for some reason, the vasculature, maybe it was the histology, we saw fewer vessels in some of the day 10ers, and that didn't make sense. But it probably could have been our sectioning, because in that way I'm counting it as a 2D metric and not a 3D one. Does that answer the question?
Uncertain.
Uncertain, yeah, that's a great answer. Any other questions? I know there are more questions. Don't be shy.
Or anyone from the public audience? Yeah, but if somebody put some light on that. But, I definitely, we can welcome, because it's a public defense, anyone online has a question.
Oh, yeah, I checked the chat and
Okay.
no questions.
You're welcome to, yeah.
Okay.
Just make sure, give time to Jean and Warren and Arvind. Great to see you here.
Yeah, I'm happy to be here. Yeah, you're kind of filling in for Sammy a little bit. So if there's no more immediate questions, you can always ask me like, oh yes, Johnny.
Yeah, one immediate question.
Okay.
Do you know that you absolutely killed that presentation?
Oh, thank you so much. Thank you so much. Okay, so in this case, I'm going to take a short break.
Okay, so we had an extremely deep deliberation and we decided that we're going to skip it. So the committee, because as research defenses go, like Becca, sorry, we took you on the side and spent half an hour there. We as committee only met like less than 2 weeks ago. So we've had that discussion. So why do all the logistics and go on?
All right, do you have any like closing remarks you want to say before? I have some final announcements, but I want to give you.
Do you want me to go first or you want to do that?
You go first.
Okay, can you go to your first slide? Very first slide if you can. That's because the first thing I want to do is to take a selfie. See if it works. I don't know if it's good enough or not. One more. I'm not just so good at it. So there you go. See, all right, thumbs up.
Thank you so much. That's
Okay.
a great picture.
All right. So, yeah, I think at this stage, as I've said, research defines to thesis. It is, in a way, celebration with gravity because much work is done. It's not a party. Later, that will be. So I want to take a little bit of time mainly for family and friends, but all the others who know Alexis to lay out a bit of a journey. And she did mention, I mean, she came, first of all, I should tell you, she came from Wellesley to MIT to some startups to kind of with a lot of good experience. And then Pfizer, Kathy Cullen, and then she was in my class. And I teach, and her background is neuroscience, biology, physiology, and I teach principles of instrumentation, design, and so on. So it starts to tell you something about Alexis. So, any questions? And Sam sitting quiet, no question. Eric, no question in those days. Alexis, always hands up. I mean, to the point where by the end of semester, I'm worried that, oh my God, she's going to get me, And so she had that chutzpah and curiosity and energy to ask questions. And she did get A+ from non-biomedical instrumentation, electronics background to do that, right? So it's a good message for anyone, everyone, you can do it. And then there was this chance to, it was an invitation from Bioelectronic Journal, there was this new journal. She put together this paper within like a month. I said, oh my God, we are scientists and a budding who for once liked to write, right? I don't know how many faculty that my students love to write, and so getting the paper out was a great start. But then, all of you have heard, right? I mean, PhD, you heard from me, the definition of PhD is paid or dues, paid is dues. And it was COVID. So let's not overlook that period. She wanted to do those electrodes, microfabrication. We had a clean room at Homewood. I even sent her to physics building, and this is in COVID with distancing and all the. So there's a lot of hardship that has got buried. It's not a failure, it's the life's reality. Everybody in the room, students or professors have felt that. Some new young people who are in the room, get ready for it because it's just hard work. And she overcame, and some of them were failures. But the rest, I don't think I want to narrate because you did an incredible job of, acknowledging Connor and Tufar lab, and then Arvind and Akanksha and the other labs. So there is, and a lot of people in our lab also, of course. I have to mention my lab. I mean, I am like busy, overly distracted, overly everything. These two cleaned up my damn lab. I mean, they are, I don't know whether it's thanks for science, but get this everything organized and orchestrated and passing all the, all of that. The other thing Alex did, run a terrific lab meeting, right? I mean, like group meeting, right? She had this real type story, like everybody got a chance to present something and all of that. And so I kind of want to convey that, of course, there is a lot of research that is, she narrated, I won't repeat ups and downs about muscle mass, go to Bayview, CT, ultrasound, and Akanksha lab. So we have to pull up. Arvind, and I said, oh my God, the imaging work you've done is itself publishable, but you do what you do, and I hope somebody will carry on that work because not just imaging, multimodality, how you put together data, Alessandro, Chiara, they all help. There's a lot more there as you recognize, and you said many times, but then you have to graduate. So all things comes to an end, and in a very good way. But I think I just wanted to narrate the journey of all the effort beyond the accomplishment that's gone in, not to overlook the fact that she had initial award from our department, training grant fellowship to a self-earned NSF fellowship, or not to overlook help with discovery grant that was funded to get some of that work started. Didn't get into it, but a year of monkey work that wasn't that easy to do. And I think Kiara probably remembers the effort and the pain. And then, we tried NIH R21, which you are very instrumental in. I just want to acknowledge that there's a lot of other things that she hasn't done, but great score, 20 percentile in 23, whatever in modern language, but today not good enough. And we live in a very competitive, difficult time. So not everything comes together, but you have done it and paid your dues. And so I want to acknowledge all that effort, well done. And for me, it's a great work and great accomplishment. So now you can do your wrap up.
Okay, good. I have one last thing I want to do before we all eat that cheesecake that I brought mostly for my. Okay, so just a few last things before I let you guys go.
The first is I have a big announcement. Some of you have heard this in like various stages of, but certainly some of the people online don't know this. Some of my family hasn't heard this. I got a job, yay. I am going to be a senior scientist at Artificial Axon Labs. Thank you so much. I'm so excited. I will be working again with my old mentor, Anna Yagilka, and I'm so excited to be working together again. The company is in Beverly, Massachusetts, which is around where Salem is. It's pretty much the same area. It's a little bit north of Cambridge, where you guys know I was working at Pfizer before I came here. And, you know, Wellesley's right there. So you can see I'm making my way north. Okay, so big announcement. Yeah, I get a job. So excited. I start May 1st. Oh, hi, family. I know some of you won't get to see me this week, but if you're feeling proud and want to like contribute, here's my Venmo. I really, really love you guys so much. Thanks for watching. And a few more thank yous. Speaking of family thank yous, I totally forgot on one of the slides to thank my on the family slide to thank my siblings, Andrea and Race. If you are still watching, thank you so much for getting this far in the presentation. I love you guys. Oh, I also want to thank my wonderful friends. I have a few of them here, and I'm just like so not only like grateful that you're just here, but you helped me set up in a major way. And other people who have been so great. This is why I came to Hopkins. I came on my interview, and it's not like I talked about some amazing research with some professor that made me come here. It was meeting people like Paul and Oliver and Matt and many others in the program who got me here. And then, of course, all my friends outside of Hopkins. I've made a real community in this area, in the Baltimore area, and made some local friends. And I'm just so grateful for that. And I don't know if also just thank the Drew organizers. Many of you know I've been organizing with Teachers and Researchers United. It's the union that represents PhD students that was voted for in my time here. So in my time at Hopkins, I've seen, you know, I've participated in several, you know, rallies and events, and even threatened to go on strike. And we got a 20% raise in pay for PhD students and other, like many other improvements to our working conditions. And that wasn't like me doing that. That was me being part of a greater body of organizers who are tough as nails and are strong like smart scientists. So thank you, true folks. I really enjoyed organizing with you. And now we can have cake. That's it. Thank you, guys.
One more order of business. So in the Stafford Lab, we have a tradition where one of the students that's going to graduate soon brings a bottle of champagne. So in addition to cheesecake, we have champagne to celebrate Alexis's graduation. And she'll sign this and it'll go up in the lab. I brought a non-alcoholic version because I don't have to drink, and an alcoholic version so that everyone can enjoy. Oh my God. And I just wanted to say that I've worked with Alexis for 4 years now. So when I came in here, she was my first mentor here. And I'll give just one short story. It's nothing to do with me, but I think it says a lot about her, which is that it was my second lab meeting here. And she gave a presentation, and right after the presentation, one of the master students came to me and was like, is she a PI or is she like, what year of her postdoc is she in? I was like, that's a second year PhD student. So I think immediately from the very beginning, she was very obvious that she was very eloquent, well-spoken, and a great leader. And obviously,
I use fancy words, and one word I use to describe plum.
Thank you so much, Tara. Thank you so much. No, right on here. I was gonna say, may our discoveries be celebrated and retaught through the years, and may word of our mistakes land on deaf ears.
All right.